Example 6 is very similar to example 2. So you just have to identify the perpendicular distance and then you are sorted. Under 5.3, which tells us you can solve problems about bodies resting in equilibrium by equating the clockwise and anti-clockwise movement. And I want to say here that when a rod is at equilibrium, then it is important to know that the moment clockwise is exactly equals to the moment anti-clockwise. And therefore, if you would wish now to talk about example 7, let's hear the question. The diagram shows a uniform rod AB of length 3 meters and a weight of 20 newtons is resting on the support, or is resting on the rod. And that rod is being supported at point A and point C. We can see the diagram. At point A we have a fulcrum or a rotating point. At point C we have another rotating point. We have the reaction at point A. We have the reaction at point C. The question is, calculate the magnitudes of the reaction at each of the supports. How then do we study the diagram? Let us first of all study the diagram. There's a reaction at rotating point A and there's a reaction at rotating point C. Between A and C, we have 1.5 plus 0.5, we have 2 meters. And then 1 meter. The whole rod is 3 meters. There is a weight 20 newtons hanging somewhere 1.5 meters from point A downwards. Now, from the previous topic, namely static, we realized that the force upwards is always equals to the force downwards if at all the particle is at equilibrium. With that knowledge, of course, we know the reaction at A, RA, plus the reaction at C will always give us the total downward force, which is 20 newtons. Having understood that, then we need to get the moment about either point A or point C. Let us take our point A to be the fulcrum. And about point A, the reaction at A will have no effect if the rotating point is A, because we have 0 distance. RA is 0 distance or 0 meters from the rotating point. But of course, the 20 newtons will have its moment and it's going to be clockwise because the 20 newton is going downwards, so it will rotate this way around point A or about point A. So let's talk about the moments. Moment about A. Moment about point A. 20 newtons multiplied by the distance, which is 1.5, then we get 30 Newton meters. That is the moment generated by the 20 newtons. Let us calculate now the moment generated by the reaction at C. And the reaction at C, because it is going upwards, then it will be anti-clockwise. It will be anti-clockwise. You realize that the moment about A, due to 20 newtons, is clockwise. This is clockwise. The moment at A, due to the reaction at C, which we don't know, is anti-clockwise, whereby RC times, what is the distance? The distance from C to A, the rotating point, is 0.5 plus 1.5 meters, which is 2 meters. So times 2 is 2 RC Newton meters, and this is anti-clockwise. And because the rod is at equilibrium, the moments clockwise is always supposed to be equals to the moment anti-clockwise. So this one gives us 2 RC Newton meters is equals to 30 Newton meters. 30 Newton meters. And we all just have to divide by 2 to get the value of RC. RC is equal to 15 newtons or 15. It is important to also note, that having realized this, then we go back to our original equation where RA plus RC is 20 newtons. So therefore RA plus 15 is supposed to be equals to 20. So the reaction at A is 20 minus 5, which is simply 5 newtons.
Minus 15.
All right?
Minus 15.
Minus 15, rather. Minus 15. Minus 15, yes. 5 newtons. Good correction there. 5 newtons. All right?